So I will just quickly summarize the formula that we obtained for the R square, both in the case of intercept as well as no intercept. So possibly the intercept case is easier to understand. So in the intercept case, you are working with RSS, which is the residual sum of square, where you are fitting the full model to y. So whatever is the predicted thing, that is yi hat, and this is the residual sum of squares. And RSS1, when you are fitting only the intercept term. Now when you have only the intercept term, you are trying to explain y using just a single constant, and that will be just the average value of y. So that you are subtracting that y bar. Again you are taking yi minus the fitted value, the restricted fitted value, square and add. And then R square will be RSS1 minus RSS divided by RSS1. So I have taken that RSS1 by RSS1 plus 1 minus RSS by RSS1. Now the very same idea is present even in case of no intercept case. RSS is still the same old value. RSS1 this time is different because there is no intercept term. So if you have removed the model, then just nothing remains. So your entire y's are explained. So RSS1 is summation yi square. R square is again the same formula, except that the denominator is slightly different. Now both these formulae are used depending on whether you have intercept and no intercept. And if you just look up Wikipedia and places like that, you will usually find R square is defined only in this way. People often tend to forget that R square is based on a general philosophy, and according to that philosophy applied to the no intercept case, the formula should change to this. Of course, R remembers that. Okay, now let's just quickly remember this structure, and then I will try to explain why some people find fault with either this or this, the very idea of R square. The problem is this. So what we are comparing are basically two residual sum of squares. We are always comparing this residual sum of square with the thing where you are not including x, which is either the entire green arrow, if there is no intercept, or with this tilted red arrow, which is supposed to be a brown arrow anyway. You can understand that it's brown. So you are comparing the length of this with either the length of these or the length of this. But the problem is the following. Observe that if I increase more and more terms, increase the number of terms in my model, in that case, this blue line remains the same. So if you have intercept, intercept remains intercept 1, 1, 1. Similarly, if you have no intercept, then you do not have any intercept, so you are basically trying to predict it with only the origin. So in either case, these things does not change. The thing that changes is this part, what I have called RSS. So RSS1 will remain the same. For intercept case, RSS1 will remain the same. It does not involve the model. Similarly, here also, RSS1 will remain the same. So whether you are taking the green arrow or you are taking this brown arrow, so these two things have the same length. It is this thing which will keep on decreasing as you add more and more and more terms, because then you are optimizing over actually a larger space. So you can come closer and closer to the actual thing. So RSS will keep on going down as you use more and more terms in your model. So as you use more and more terms in your model, this fellow is decreasing, this remains fixed, so R square will keep on increasing. It will keep on increasing, both here as well as there. Now that is not always desirable, because suppose I have fitted a model y I equal to alpha plus beta xi plus epsilon, and this is an adequate fit, but I just throw in for good measure xi square and xi cube and all sorts of things. Then I am just reducing RSS. So do I want to say that this model is better than that model, whatever be the case? There is no doubt that even if you have a linear regression, so your original data actually comes from a linear thing, just by adding more terms, it will reduce RSS to some extent. right? So this teacher seems to indicate the bigger the degree, it is always better and better fit. But somehow we should take into account the fact that in order to get this better fit, we have to spend two extra parameters. So is that additional reduction in RSS or the additional increase in R square justified when we have to spend two extra parameters? Now, how do we really compare the two things? One is increase in number of parameters, or I might say increase in the rank of the design matrix, and the other thing is reduction in RSS. So the two things seem to be quite incomparable, right? So how do I do that?